computer. All right, now I can share and go to that, share, and I can enter full screen, and there I am. Okay, so I'm going to give just a little bit of history starting about, I don't know, 600 BCE or something like that, and do a real quick cover of what went until we get to Faraday. And I'm going to cover Faraday almost entirely, a little bit on Thomson, and only a touch of Maxwell. Maxwell would be the next one. Okay, so come on. There we go. So we're doing physics in the 19th and 20th centuries. So we're starting with, here's the thing that everybody always knew about, which was lodestones or magnets with iron filings on them. In the middle of what I plan to get to, we'll go to the bomb work in the 40s, and we'll wind up at the 20th century. And one of the things that's fairly important about that is the perturbation theory method created by Dirac and recreated by Feynman. And that's his van, and he used to drive around with his pictures on his van. So this is a quote. I usually start with a quote. While other sciences search for the rules that God has chosen for this universe, we mathematicians search for the rules that even God has to obey. So this is Fields medalist, French mathematician Jean-Pierre Serre, and he's gotten a lot of awards and is quite famous. All right, so we're going to start with the really early discoveries. So about 600 BCE, there was a Greek philosopher, Thales of Miletus, or I don't know how you pronounce. Anyway, noted that amber attracts feathers and other lightweight materials when rubbed. This was, as far as we know, the first written reference to static electricity. Of course, history always depends upon what you can find. So if somebody had discovered it before and didn't write it down, we wouldn't know. So he also experimented with what are called lodestones or magnetite, and observed that it can attract iron. Now, about 100 BCE, the Chinese, the fortune tellers in China, used lodestones as divining boards for telling what the future was going to be. And in 50 BCE, the Roman poet and philosopher Lucretius related about the physical theory of Greek philosopher Epicurus. And in his poem De Rerum Natura, on the nature of things, and he tried to explain the activity of magnets or lodestones. The Chinese, of course, were the first to use magnetic lodestones for compasses. And the picture you see on the bottom is a sailing compass for the Chinese. So, and the report of that is in a Dream Pool essays by Menqing Pitang. I don't speak Chinese, so I don't know. Anyway, and it was done by Shen Kuo. Okay, so we are now getting into the positive, the real after BCE. In Europe, we caught up a little while, about 100 years later. Alexander Neckham, who was an English monk, gave an account of using magnetic compasses by mariners in his text on instruments, about 1180. Compasses in Europe. Looks like I wrote that twice. Columbus, during his westward voyage from Spain, he observed a very strange thing. The declination of the magnetic needle in his compass changed half midway across the ocean from easterly to westerly. Didn't understand why, but found that. Cardano, he was an Italian mathematician. He's the one who solved for cubic equations, the roots of cubic equations. And he recognized that magnetism and the attraction of small objects to excited amber are not the same thing. They're distinct kinds of effects. And Italian geographer Livio Sannuto first noted that the Earth has two magnetic poles, a north and a south, about 1588. Ole Romer, an astronomer, did the first approximate velocity of light by observing the periods of a moon of Jupiter when the Earth was approaching Jupiter versus one that it was going away. The period seemed shorter, so he used that to estimate the speed of light. Charles Dufay in France found that there were two kinds of electricity, and Ben Franklin later labeled them plus and minus in the wrong order, but that's the way it goes. It has stuck. But like charges repel and unlike ones attract. The Leyden jar was created in 1745, and then this is not anything to do with electromagnetism, but in 1687, Isaac Newton created what he called the law of universal gravitation, that any body attracts any other body in a straight line, connecting them instantaneously, that is non-local. Newton was criticized for introducing occult agencies, i.e. magic, into science because of his postulate of an invisible force able to act over vast distances. Now, in a letter, he said this idea was so absurd that no reasonable person would believe it. But he left the solution to this problem to future natural philosophers. For him, hypothesis non fingo. And in 1752, Ben Franklin introduces the lightning rod and suggests that lightning is just a great big electric spark. Finally, about 1777, Charles Augustin Coulomb was awarded a prize for accurately measuring the force between magnetic poles at a distance r, and it was proportional to 1/r squared. And he later modified his instrument to show that between electric charges, they had the same 1/r squared dependence. And by that time, because of all of the great successes in astronomy, everybody just assumed that the same thing that had earlier been called sorcery was how everything just worked. So all natural philosophers assumed that everything was straight line and instantaneous and inverse r squared.
When did the word electric pop up?
That's a good question.
Oh, later, we'll check that.
Yeah, I looked at, I saw it was while I was reading, but I don't remember. It was sometime, well BCE,
Okay.
probably the Greeks or the Chinese. I don't remember.
Brought in the word electric. Okay.
Yeah. Yeah. Okay. So, yeah. So by 1800, everybody assumed that everything was instantaneous and across straight lines between everything. And this was the prevailing thought for all natural philosophers until Faraday. Okay, Luigi Galvani found that when dissecting frogs' legs, a touch of metal caused the muscles to twitch. And Alexandro Volta showed that Galvani's twitch was caused by a chemical reaction between metal and salty liquid. He invents the electric cell, the first battery, or the voltaic pile. Finally, around 1807, Humphrey Davy, he's an important person. He was head of the Royal Institute in London. He separates metallic potassium and sodium by running an electric current through potassium chloride and sodium chloride salts. They were heated until they melted. So he was a great chemist and also a teacher. He would give lectures about what he had found to the public. Okay, any questions? All right, now we're getting finally into Michael Faraday, Thomson, and Maxwell. And lines of force, which the people in Europe thought was the ether, Faraday thought it was a field. There's a difference there, but okay. So physics then and now, we tend to think that this is the way the world is. There's all these various kinds of excitations of different fields, quarks, leptons, bosons, Higgs, etc. And there is computational things to do in order to calculate various probabilities of things. That's what the Feynman diagrams is about. It's about a calculation. And all of the nonsense that people talk about, virtual particles jumping in and out of space, etc., is just that nonsense. There is nothing jumping in. If you actually read the axioms of Dirac and von Neumann, they will tell you that you can figure out how to set up an initial quantum state. Then the only thing you will find any information about is when you do a measurement, and you will get depending upon the basis that you use in the measurement, you will get various possibilities of things that you will measure, and there will be probabilities associated with those. That's everything that you know about quantum field theory and quantum mechanics. There is absolutely all of the stuff that people make up about things jumping around, having stuff going on in the vacuum. All of that stuff is just color. It has absolutely no physical content. Okay, so particles are not exchanging particles in the vacuum. They're not strings. And in 19th century physicists, they wouldn't have looked at any of this as being reasonable. They would have said bollocks, wrong, wrong, wrong. So they had completely different ideas about the fundamental entities that made up the world. And yet we still use their equations. So the equations are the same that we use from their time, but we have all of this different color, how to do the calculations. All right. We also do physics about who it was and where they did it very differently in the 19th century than we do today. In the first half of the 19th century, people who worked on physics also worked on chemistry, mathematics, astronomy, physiology, you name it. They just covered everything. And the term was natural philosophy. So most of this research was not done in universities, but in separate institutes or academies. And the academy was not the university that we think about today. And most natural philosophers were not professors. They weren't people, they may not even have attended university themselves. So the big shift towards research conducted in universities began around 1850 or 1870, something like that. So you shouldn't assume that the physics or physicists of earlier times were like anything that we might think of today. Any questions?
But most of them were relatively wealthy or underwritten by somebody who was wealthy, right? And developing their little labs and doing the experiments and the traveling they did.
Yeah, for the most part. I mean, Faraday was the complete, uh, he was not at all wealthy. He'd been, his father was just one rung above the real poverty that there was in England. His father was a blacksmith. So Um, he the only education he got was some minor, uh, grade school stuff, and uh, he left school when he was very young, and so uh, he was rags to riches. That that was his story. But you're right. Most of the people either did their own research out of their own money or had various people uh, paying for their research.
How did this idea of particles uh, streaming into existence and out of existence in the vacuum take hold? Who was responsible and why wasn't it rejected earlier?
Well, if you go back to uh, the Feynman diagrams, they're pictures, and they look like you got time going up and electrons going right, and they're exchanging photons. That's the story, but that's just a story. It has no physical content. That is a way, it's not even the right way to do the calculation. Feynman always thought in terms of particles, and he had to do it not in particle, but in momentum space. And he didn't know exactly how to do that from his pictures, but the great Russian Lev Landau sent him a letter saying, "Idiot, it's just uh, Kirchhoff's laws. You can do your momentum space as a dual, just as voltage is a dual to current in electricity." And that was the way in which finally um, all of the calculations could be done in quantum field theory. Feynman, he thought in terms of particles, but this is all just a story. It has no physical content, zero.
Interesting.
Okay. Michael Faraday um, became to be the most successful and famous natural philosopher of the 19th century. As I've said, he was a remarkable rags to riches story. He was born into a poor family, never attended anything close to high school, never mind college. Coming from his social economic background, Faraday said he attended a common day school. His education was of the most ordinary description, consisting of little more than rudiments of reading, writing, and arithmetic. When he was 13, Faraday was employed first as a newspaper and errand boy for a person, George Rabot, and Rabot was a bookbinder, and he was very good at what he did, and soon he became an apprentice bookbinder. Now, people would bring their books and get them bound, uh, either because they didn't like the current binding or because they were worn or whatever. So he gained a passion for science. He would read the books that people would bring and ask them to be bound. And he first found uh, encyclopedia that somebody was getting bound, and he read all of the things in chemistry and physics, etc., in the encyclopedia. So that was his initial. He was always completely self-taught. So there were various people who would give lectures, and his home was near a part of London called Blackfriars Bridge, and a local silversmith gave a series of lectures from his home. And those lectures were open to everyone on the payment of 1 shilling. So Faraday could afford the attending the 13 lectures at 1 shilling per lecture. But we know most of his notebooks he bound himself and produced for his own record. He always kept in immediate, beautiful notes for everything that he went and watched. And it was the creation of the first 4 notebooks that he had, that he showed to his employer, Ravoux. And Ravoux saw that he was very interested in science, and Humphrey Davy at the Royal Institute was about to give a lecture. Unfortunately, this was just completely out of Faraday's cost. I mean, he could not possibly pay for going to such a lecture. So Ravoux bought the tickets and gave them as a gift to Faraday. Faraday went to the lecture and took elaborate notes, had them written, all kinds of figures about what was being said, the instruments that were used, all of that stuff, and took this and created a beautiful volume, since he was a bookbinder, and used this to meet Humphrey Davy and give him a copy of this volume. Davy noticed that he was quite smart. He was able to do physical things. So within a couple of months, he'd been employed at the Royal Institute. He was just an assistant doing physical things that Davy was doing, but that was his start. And the rest, as they say, is history. So Davy and Faraday worked together almost daily for several years. And eventually, when Davy stepped down, he had Faraday become the director of the Royal Institution. He just said, "You're good enough, you can do this." And Faraday continued the work on chemistry, optics, electricity, magnetism, electrolysis. So the picture on the left is a drawing of Faraday in his lab. And there was a religious connection to Faraday. He was a part of a small Protestant sect called Sandemanians, and they emphasized the underlying unity of all nature and of all people and all things. Everything was connected with everything else. And Faraday thought that the same thing should be an approach to nature. So he was fascinated by the interconvertibility of forces. And that was where he started his work. He did several things following Davy's initial stuff. He delivered a Christmas lecture for everyone at Christmas, and for the most part, because he had been not able to pay to go and hear Davies, he made them very cheap so that anybody could come to his Christmas lecture. So much of Faraday's work centered around what most people called the ether. He wasn't sure what it was, but it was a medium filling space that enabled distinct physical processes to affect one another, the interconvertibility of forces. So why did people think you needed an ether? Well, around 1800, Thomas Young had shown in various experiments that you could have, if there were waves, you'd have constructive interference or destructive interference. And he showed various experiments and showed that light had the effect of a wave. So people said, okay, what are waves? Waves are in water, waves are in air, waves are in some kind of a media always. So light, if it's a wave, it's got to be in something. So they made up this term, luminiferous ether, and lumen means light, iferous means carrying. So it was the light carrying medium in which light traveled. So as I said, one of the other experiments that were done was French physicists had shown that the speed of light depended upon the medium in which it traveled. So if it was slower in water than in air, or what they considered to be vacuum or the ether. So you have an index of refraction. If you're looking at water, there'll be an angle between you and there'll be an image that you'll see that's not actually there. And we use Snell's law to show that effect. So again, another kind of set of experiments for why the ether must be a medium. There has to be some lowest index of refraction. So that was why everybody thought that they had to have a luminiferous ether. Oh, yes. Today we would say trending, the compass moved. So much for light. What about electricity and magnetism? Well, Ørsted was doing an experiment, Hans Christian Ørsted, and he accidentally didn't mean to do this, but he discovered that when there was an electric current, the image on the left is a picture of his stuff. The stuff at the top is a battery, a pile, voltaic pile, and then there were, of course, some wires and a current going along the wire. And he happened to notice that a compass would be deflected when the current went by the compass. So that's why I said compass moved. So that meant electric currents could induce magnetic effects. And this became a headline throughout Europe. Faraday, this seemed to be exactly the kind of interconversion of forces that he was so interested in. Within months, Faraday had replicated Oersted's findings and also discovered the inverse. If you had a rotating magnet and you had a coil next to it, you could get um, a voltage going back and forth. So electric currents could induce magnetic effects, and moving magnets could induce electric currents. That was one of his first discoveries, induction. He used this later to make the first motors and the first dynamos, that is, electric generators. So he was quite a important inventor as well as a theorist. So while he was investigating induction, he began sketching what he considered helpful doodles, or what he called lines of force. And he felt that if this was an underlying fluid, then there might be some kind of tension in the fluid, tension, compression, whatever was happening. And he thought that these lines of force would represent the states of tension in this fluid. So the number of lines radiating outward from positive charge, or was radiating out from the positive charge, the number of lines was proportional to the magnitude of the charge. And the density of the field lines, because they're going out in rays, would fall out as 1 over r squared. We today think of this as Gauss's law. So if you had these intersecting a sphere at any given radius, then the number of density would scale like n over a, and a is 4 pi over r squared. So if you take a look at electric lines from positive and negative, they'll come back to each other. That's on the right, an electric dipole, and like charges would repel. So Coulomb had shown that there was a constant times the charge on one and the charge on the other divided by r squared. So the equation at the bottom on the left was Coulomb's law. Lines of force, more doodling. So he did these lines of force, and he thought about them as being states of tension in the fluid. So we think about them as being real. And this is an image of uh, a bulb of oil with a bunch of seeds in it. And there's two charges, one positive and one negative. And you'll notice that if you take the left one and rotate it so that it's up down, you get the same picture as what you get in the seeds. So electric, you normally see these things in magnetics with iron filings, but you can do it in electric charges and fields with various kinds of seeds. So the force, again, is proportional to 1 over r squared. Magnetic lines of force would diverge from a north pole and converge to a south pole. And you usually see that either drawn from the force lines, which are also proportional to 1 over r squared, and they converge. So they go from one side to the other along curved lines. And this was another break from Newton. Everybody thought that everything was shortest distant lines between points, instantaneous. In Germany, there must have been, I don't know, 20 different versions of this kind of structure for electricity and magnetism. And you could just see it with either the seeds or the iron filings, but everybody assumed had to be instantaneous and straight line. People don't even look. So the next thing that Faraday introduced was the idea of a field. So the electric and magnetic fields described the state of the fluid, which people in Europe thought was the ether and was represented by the local lines of force. The forces produce stresses or tensions in the fluid or field at a particular location, and then that state of that would change over time. So not instantaneous, but local. So with all of this stuff, he finally decided that lines of force were real. And he thought of a decisive experiment, an experiment to prove that they were actually real. So it was a physical substance, the field. And he decided that if it was real, then you would rotate the plane of polarization of light if you put it in a magnetic field. And that is now known as the Faraday effect or Faraday rotation. And to Faraday and his peers, this was striking evidence that the ether must be real. The B field, the magnetic field, was twisting strain in the field. This was a kind of torsion, and it deformed the material medium within which the light traveled. So, and at this point, this is 1845, so it's relatively late in his career, but this was the final thing that showed that the field was real. Now, Faraday didn't think very much of math. I do not remember that maths had predicted much. Perhaps in Ampere's theory, one or at most two independent facts. I'm doubtful of two. Facts have preceded the math, or where they have not, the facts have remained unsuspected through the calculations. And sometimes when the fact was present, the calculations were insufficient to illustrate its true nature until other facts came along and to help. So he didn't think a whole lot about mathematics as a way to do physics. We're going to find that Thomson and Faraday were very much different. Okay. So Michael Faraday, he worked on, this is the summary of what we've done. He worked on a lot of natural phenomena, chemistry, optics, electrolysis, electricity, magnetism. The things we've been focusing on is electromagnetism. He did a lot of other things as well. And he was particularly interested in the interconvertibility of forces because of his religion and the fact that he thought there was an essential unity of nature. He'd never been trained in mathematics. He was an apprentice tinkerer and inventor and became a leading experimentalist. He only worked at the Royal Institution. Now, the British government thought he was amazing. He'd been made the head of the, I can't remember the name of the Royal Society of Natural Philosophy, something like that, a very major group of natural philosophers. And the government was very impressed by everything that he did. They offered him a knighthood. He turned it down on religious grounds. And he also didn't want to be able to benefit by making money. He thought that was not something he should do. So the government had these sinecures that they'd do for people. They'd create buildings and they'd do all the maintenance, they'd do all of the servants, etc. So they built a house in London for Faraday and gave him till he died in that building. Today it's a museum called the Faraday House in London. Okay, so he introduced this idea of lines of force and fields. And this was what Einstein thought was the greatest creation in the 19th century physics, the fact that the field was created. And he thought that the field was a all-pervasive fluid, a medium with which various kinds of forces unfolded. And in place of Newtonian action at a distance, he tried to explain all physical phenomena in terms of local fields. and they would convey effects point by point throughout the medium. What I'm going to do is quit the share right now, and then there was a Royal Institute film that was created in 1930, doing one of the anniversaries of the Royal Institution, and I'm going to show that film. So hang on.
Are you going to keep your recording on?
No, I was going to shut it off. Okay. Let me stop the share. Okay. Let me go to Zoom. Oh, come on. What are you? Oh, I got to get out of that. All right. Now I can get into this. I can stop